good afternoon, everyone, and very welcome to the combinatorics talk. And it's a pleasure to introduce Professor Bela Bollobas, who is he has done a great effort to be here with us today. So it's a special thing from us all in the audience, and especially from the organizing committee. So a few words I would like to say is that, well, as you may know, he was born in Budapest, Hungary, and he has been living in the UK for more than 40 years. After being a student of Edwards in Budapest, he came to Cambridge to study with Adams, and since then he has been made fellow of the Royal Society, and he has had more than 50 PhD students, many of them so successful that he won a Fields Medal. And so this mathematical side, but he also has a very athletic side because he's a pentathlon athletics. And also, I would like to remark that his wife, Gabriele, is a famous sculptor who's made works for many people, also a bust of Maestro Machiavelli, as in the gallery. So that's enough of introduction. Thank you for being here.
Thank you very much. I'm really the man from the moon. I'm really an alien. Nobody is working in any of the fields I'm going to talk about, so now I'm standing here trying to entertain you, and you can come on, entertain us and tell us something which is very difficult and extremely easy to understand. It's not always possible. Actually, first a disclaimer. I'm down as a combinatorialist. Yes, I'm very much a combinatorialist, probabilistic combinatorics and lots of other things. But my topic today, bootstrap percolation, is in fact not in the realm of combinatorics. Recently, combinatorialists have taken a lot of interest in the area, but originally it was very much in statistical physics and the probability theory. So really lots of probabilists used to do bootstrap percolation, and the origin goes back to mathematical physicists. Okay, so let's start with one of my heroes, Johnny von Neumann, who introduced cellular automata in the 40s and 50s, and Ulam was never shy to tell us that after his suggestion it happened. So it's a very simple dynamical system. Usually we have an array of objects, sites, which are somehow connected. They have neighbors and near neighbors and far neighbors. And each site is in usually one of finitely many states. Quite often, essentially all the time, it's enough whether it's 0 and 1, alive and dead, healthy and infected, whatever. And once every site is put into a state, we have a certain configuration, the system starts to live its own life. It updates at every time step, it updates itself according to certain rules. In the simplest case, these are nice deterministic rules. The main thing being that the next state of a site depends only on the states of nearby sites. So not the whole system affects it, but just nearby. Which is the most famous cellular automaton, Conway's Game of Life, which at the latest count, if you Google it, you get 3 times 10 to the 9 hits. Just imagine the number of hours mathematicians spent on it. Actually, in the early 70s, Conway could be found in the common room in Cambridge with his groupies trying out various configurations. What happens? Okay, what we have actually is something much easier than the Game of Life, which is of course not a game; it's a cellular automata. We'll be interested in bootstrap percolation. Again, in its simplest case, we have a single parameter R, and then there is a graph with various vertices, which now we call sites because we are we have been infected by physicists, these sites, every site is in one of two states, let's say healthy and infected. And once it's decided which sites are infected, the infection starts to spread. At every time step, a site becomes infected if it has at least R infected neighbors. A site which is infected remains infected forever. That's incredibly important. That simplifies things enormously. If we have recovery, then it's a different ballgame. Okay, and it goes on, so the infection spreads to bigger and bigger sites. If everything gets infected at the end, then we say that the original set percolates. Okay, and of course introduced by physicists. Now, there are lots and lots of examples. Totally the basic example is the n by n grid. You've got n squared sites, and every site is in one of two states, okay, infected or healthy. And once you decide which states are infected at time 0, at every time the system updates itself, the easiest is to take it with two, not the easiest, the only interesting case in the case of n by n grid, if you become infected if you have at least 2 infected neighbors. Now, of course, this has a boundary, and the boundary effect occasionally upset the apple cart, and unnecessary complications come in. So you may as well take the torus and do it there. Okay, let me just, whatever we do, we have to be sure that we, I mean, I'm afraid I always allow it. In fact, I want to say I will allow it until eternity, but it doesn't take any notice of it. So okay, so now let's take a 16 by 16 grid, and the greens are the infected sites. So now let's take it slowly. I mean, the blue ones are those which have 2 infected neighbors, so at the next time step they become infected, and so on. And then the whole thing very quickly, we are on a torus, so the top thing comes back again. Okay, let's finish it because there isn't any point in. So that's what we get. Okay, or let's take it fairly fast and give it again. Now we had infection, or let's take it on 512 by 512, and these are random sites chosen with probability 0.3143. So what happens? Okay, here we may as well go fast. Various seeds grow, and then the whole thing dies. That's what happened. Or let's take it a little bigger probability and see what happens now. It grows in various areas, and then everything is dead again. So we didn't get percolation, although this is about it. Okay, now here it will percolate in 1 second, of course. Yeah. Okay, so I hope if nothing, you will know what bootstrap percolation is. Now, of course, we can take infinite ground graphs, and you know percolation theory is always on infinite lattices, infinite graphs. So the natural thing was at the beginning to take it on the infinite lattice, but we can also take it on finite ground graphs. The basic idea, the basic example is the d-dimensional n by n by n grid, or the similar torus. There are lots of variants, of course. What we have just taken was the simplest example. Again, just about the simplest variant is the so-called modified bootstrap percolation, which really was invented to make the problem solvable, which otherwise would not be solvable. So the rules are pretty similar to what we had, but the site will be infected if at least one of the two sides above it and below it. At least one of these two sides is infected, and one of left and right sides will be infected, in front and behind sides. So we have got in d dimensions, we have got these d pairs of neighbors, and every pair has to be such that at least one of them must be infected. So again, in the cheapest way to infect the site if it has d infected neighbors, but of course, why does it want to go? Sorry. But of course, you may have lots of neighbors, and still, I'm sorry, where should I stand? So the trouble is even having slides to project is such a pain. I mean, it's so much against the nature of mathematics. And mathematics should be all about thinking and writing on the board and making mistakes there. I think it's pathetic that somebody stands here and flips and tells you, ah, that's why it is. Yeah. Anyhow. So.
I say, you could have given a blackboard talk.
What?
You could have given a blackboard talk.
Not about this.
Well, I understand
Can you imagine?
You need your computer to do the pictures, right?
Oh, no. Even then, I mean, the whole thing is the whole lecture is a bit like what I would do in Cambridge for the very first of a Part 3 course. Except there, of course, I will use the board and I will actually prove things. So. No, here, unfortunately, I am constrained. Okay, so now we know what bootstrap percolation is, and in any kind of area there are two obvious questions in combinatorics. One, a set of extremal questions, and probabilistic. Now, historically, probabilistic came first, very much, but in some sense, extremal is maybe more natural. So let's start with these extremal questions. Okay, in this basic example, n by n grid, at least how many infected sites do you need to get percolation? And that's not a joke. I mean, it's a genuine, tiny question. I mean, it's hard to call it a regular question, but okay. So if you take all infected sites down the diagonal. So if your infected sites are those along the main diagonal, then at time 1, the things next to the diagonal will be infected, time 2 next to it, and so on. So in n-1 steps, everything will be infected. So of course, n infected sites will do, properly arranged. The question is it, sorry, where are we? Can you do it with only n-1 infected sites? So the question is not n will do, of course. Can you prove that n-1, of course, will not do? Actually, who has seen this problem and who knows how to do it? My goodness, just 2 in the whole room. And in a way you are very lucky, very lucky, because you will get a lot of pleasure out of doing this easy coffee time problem. But it's elegant, but do it. Don't forget it. Okay. So of course the answer is n will do. And in fact, we can also it's also true that whatever infection you take, it sort of ends in the corners. Now, what's the answer in modified bootstrap percolation? Of course, it can't be smaller than in real bootstrap because it's harder to percolate in modified. So if the answer is n there, then it's n here. But here, the proof is totally trivial. And that really is totally trivial. Everyone who is not asleep can tell me why it's trivial. Come on, no, please. So modified, when do you get when will a site be infected? if one of the sides above it and below it is infected, and one of the sides to the left and to the right is infected, and one of the sides in front, I'm sorry, we are two-dimensional, that's it. Okay, so what happens if you have an empty row? If all sides in a row are healthy, that's it. They will never be infected because they would need at least one infection there. So that's a non-starter. Okay, what about largest minimally percolating sets? So can you get many sites which altogether percolate, but no matter which site you delete, recovers, becomes healthy, you do not get percolation. That's a different ball game. Totally different question. Actually, it's not known, but it's known that it's some constant times n squared, and even this proof is pretty non-trivial. Okay, variant. What happens in the n-dimensional hypercube? So you have 2 to the n sides, and arranged as in the power set, or 0, 1 to the n. That's it. Everything has n neighbors, and you take this 2-neighbor percolation. What's the answer there? So how many sites can you have that they percolate, but no matter which one you delete, you make healthy, you do not get percolation. Now, that's how the beginning goes. The n plus 1 is, of course, silly. So let's say between dimensions 2 and 10, the answer is n. So what should the answer be? Of course, it's clear it should be n, which is not quite the case. Reed will show that actually it's exponential. You see? So it's about 2 to the n over 4, the answer is. And what is surprising that in this case it could be determined exactly, while in the case of the n by n grid, which may look easier, it's far from it. So this is a much easier question actually. Okay, what about the shortest time? Again, so how, if you take n infected sites at the beginning, how quickly can you get full infection? The diagonal shows that you can do it in n-1 steps. Can you do it quicker? Again, the answer is no, you can't. This is again a lovely coffee time problem, but much less trivial. So if you can do it, congratulate yourself. What about booster percolation? Non-starter. Non-starter. Okay, what about longest time? We just changed shortest time to longest time. Of course, there are two variants. We may say that take n sites that percolate, that's the minimum number of sites that percolate, or take any number of sites that will percolate. And how long, how many steps do we have to take till full infection? And again, this is far from trivial. It was done by two very clever students. One of them has got his PhD, the other one is about to get it, submitted it yesterday. That the longest time in an n by n, starting with n, is 5 and n squared over 8. It would be very natural to assume that how do we make sure that it takes a long time to percolate? That we start with as few as possible. And that's not the case. If you are allowed to take any number of sites, then it may take even longer. And the number of, I think I did it. Anyhow, the number of infected sites you need at the beginning is 23 and over 18. Okay, in modified, the answer doesn't look trivial, but it's not a problem. What about higher dimensions? Of course, all these questions remain in higher dimensions, and then we have different problems. If we are in d dimensions, then the case r equal to 2, so infection parameter 2, the one I have been considering up to now, tends to be much easier than the rest, and the only exception is r equal to d. So at the when you infect as many as the dimension, or you infect, or you need 2 for infection. So in these 2 extreme cases, it's much easier than in the middle. For example, if R is equal to D, then again it's quite easy to see that you need that many infected sites for full percolation. In fact, in this case, that is easier than to show that there are configurations with that few infected sites which work. Okay, now just I'll give you actually three problems. One of them is the one we have here. Just a slight change. We changed the infection parameter from 2 to 3. And let's just take the cube, 2 to the n, the hypercube, 2 to the n. The sites, or if you like, the power set, the set of all subsets of a set of n elements. And this site becomes infected if it has at least 3 infected neighbors. Okay, how many do you need for full infection? It's ridiculous, but we have no idea. What we do know that we need at least n, trivial projection argument, and we also know that we can get away with, we can get full infection with about n squared over 6, or if you like, n choose 2 over 3 plus 1. But we know nothing in between. So it's ridiculous. So the lower bound is n, the upper bound is n squared, and we have no idea whether it's little o n squared or genuinely more than n. Bela Bollobas, with whom I worked on such questions a lot, and I conjectured in a paper some years ago that it's about n squared over 6. But nobody has come close to it. Nobody knows anything better than n and between n and n squared. Okay, now the main, as I said, the main reason for introducing bootstrap percolation is to study what happens in the random case. So let's go and let me tell you a few things about the beginning. So you have some ground graph on which you will play your percolation, and let's say an infection parameter R. And now you don't choose the set of infected sites yourself in an extremal way, but you let nature take its course, take some probability P, and choose every site at random with probability P independently of each other. And you have got this random start. Question is, do you get percolation or not? What is the probability that you get percolation? And really the main reason why one cares so much about it, because there is a phase transition in this problem, in this dynamic process. If you define the critical probability, for example, with PC, as the value of P at which the probability of percolation is exactly 1/2, may as well be exactly 1/2, makes no difference, then what happens if your infection probability is a little smaller than this PC, then the probability that you get percolation is extremely small, and if it's a little bigger than PC, it's extremely large. So you get, draw a bit, provided that you can find a piece of chalk, which is unlikely in this case. No, okay, so let's leave it. Yeah, so what happens that around PC, if you increase the probability of choosing an infected site, then the probability of percolation undergoes a sudden jump up to a certain point. It's essentially 0, and around PC it jumps up essentially to 1, and there it remains. Of course, we don't really mean on one graph. We are always interested in sequences of graphs. Sequences of graphs with more and more vertices, families of graphs we are interested, and that's how it is. So the basic question at the beginning is what happens, what can we say about this critical problem? Okay, what's going on if we take z to the d, infinite graph, infinite lattice, d-dimensional lattice. Every side has 2d neighbors, and we take infection parameter r. What is this critical probability? That's not a good idea. There's nothing interesting going on. We fall flat on our face if we try to do it. Because if the infection parameter is less than, is at most d, then the critical probability is 1. If it's greater than d, it's 0. Is it clear what this means? It means, so for the first case, if you infect the site with probability p less than 1, like 0.9999, then the problem, if swap 0 and 1. Of course, I mean, when is it easier to get infection? If you have fewer, if you need fewer sites. So if you take, for example, if you infect a site, if it has 1 infected neighbor, what do you need for full infection? Okay. One. You need just one point. So of course, if you whatever probability you take, you will get your point. And it should be the other way around. So it's 0 and 1.
No, I think it's all right. If r is less than d, that means r allowed to be 1. D could be like, you could be in dimension 4. And if r is 1, then your r is less than d, and you're in the case, the top case.
No. It whichever. The first thing should say that whatever probability you take, you get infection. If the probability is bigger than 0, you get infection. So then the critical probability is 0.
Oh, I see. Because that p is the critical probability, you say?
Yes.
That big p, that's a critical probability. Right.
Yes, that is the critical. Oh, I'm sorry. No, you are absolutely right, because you see what I have written. I don't see what I have written.
that big P.
No. It's totally correct what you are saying. I thought I was talking about. I had the critical probability there. No. So take any probability between 0 and 1, strictly between 0 and 1. If the infection parameter is at most d, it's guaranteed you get infection. Probability 1, you get full infection. If the infection parameter is bigger than d, you do not get infection. Guaranteed. Probability 1. Why? Which of these two assertions is trivial? One of them is trivial, but trivial in all capitals.
The second one, because you can have more than d neighbors.
Thank you. The second is trivial, because if you just find a little cube of 2 to the d healthy sites, then they will never get infected. Correct? You have 2 to the d infected sites. Each of them has d healthy site. Each of them has d healthy neighbors. Each of them has only d infected neighbors. They will never get infected. A little group of 2 to the d healthy sites will remain healthy forever. But of course, it's probability 1, you do get these, because you can divide your lattice into these independent, disjoint little cubes, so you get independent events. So the second is a non-starter. The first is a little bit. What truly amazes me that for quite apparently the physicists thought, because the simulations didn't tell them that they were in a trivial case. So what's the moral of this tiny result? That infinite lattices are the wrong ground graph to take. That's not where you should study bootstrap percolation. Rather on the grid, for example, n by n by n d-dimensional grid. Sometimes pointer. Oh, I forgot to ask something to. If you can't hear me, please shout. And also, if you have any questions, do ask, please, please. I mean, of course, I mean, it's terrible that Professor McDuff has to help out because everybody, all the young people are just sitting politely. You shouldn't be polite. You should interrupt and say, oh, that's wrong. You are talking about the wrong thing, which I was. Yeah. Okay. So now, same thing. We take a finite ground graph and we take the P, the probability of infection, at which the probability of percolation is 1/2. That's the critical probability. And as I said, of course, we don't want the question on one graph. We don't care what happens on one particular graph with 10 to the 100 vertices. We care about what happens on a sequence of graphs. And so what we tend to take is a sequence of graphs, let's say with Gn, and we say that phase transition occurs if whenever Pn is substantially, or even just a little bit, depends what we can prove, less than the critical probability, then the probability of percolation tends to 0. If we are on the other side, it tends to 1. Okay, let me not illustrate it. Now the basic result, which woke people up, physicists, which woke up physicists, that actually the finite case is the interesting bit, is this result of Eisenman and Lebowitz, two statistical physicists, who proved that on the d-dimensional n by n by n grid with infection parameter 2, the critical probability is about some constant over log n to d minus 1. In fact, they proved more in the sense they showed that if you take some small c and your infection probability is less than the small c over log n to d minus 1, then the probability of percolation tends to 0. But if you take a large c and your p is bigger than this c over log n to d minus 1, then it tends to 1. Phase transition in, but of course the values are not defined. Okay, it doesn't want to go on. Happy to go back, but not. Okay, so at the end, I would sketch a proof of this somewhat sharper result that actually 1 over 20 and 2 would do, but I doubt it. So let's say here we have it with concrete numbers. So if the probability is less than 1 over 20 log n, then we don't get percolation in just 2 dimensions, and if it's bigger than 2 over log n, we get percolation with probability tending to 1. Okay, now what happens with larger infection parameters? That's completely different proposition. It is much harder, and not surprisingly, so it took over 10 years of effort for Cerf and Cirillo to prove it in the case of 3 dimensions. and infection parameter 3, the only interesting thing. And a little later, building on those ideas, Cerf and Manzo proved that the critical probability in this weak Eisenman-Leibowitz sense, no concentration, no concentration whatsoever, is some constant over r minus 1 times iterated logarithm, not base r minus 1, iterated logarithm raised to the d minus r plus 1. And of course, they left open the question whether theta can be replaced by some constant. So could it be true that there is some constant, that if the probability of infection is less than a different constant, a smaller constant over that, the raised to a power, then you don't get infection and so on. Is the sharpening clear? Whether you could replace, what the theta means that if you put here a small constant, it goes one way, a large constant, it goes the other way. The question remains, can we have just one constant up there, that if you add to it a little bit, you go one way, take away a little bit, you go the other way. And actually, that is indeed the case, and in the easy case, in the case r equal to 2, it was proved by Holroyd, and it really, at the time, I mean, it was very much a spectacular result, because people didn't really expect that it could be done, and the constant is pi squared over 18. So the cutoff is sharp. So is the result clear? So take any constant less than pi squared over 18, choose sites with infected sites with probability c, let c over log n, and then let n go to infinity. The probability of percolation tends to 0. And take a c bigger than pi squared over 18, pick sites, infected sites with probability c over log n, let it go infinity. The probability of infection goes to 1. Okay, and recently, Morris, after several, after continued work of Grabner and Holroyd, proved that in fact the second term is about log n to the 3 over 2. Okay, what about constants in all dimensions and all infection parameters? That was the end of it. Again, longish story. After several papers, I proved it with Yoshi Balog, Rob Morris, and Dimitri Copain, that there is some lambda for which this thing happens. But not only there is some lambda, not only is there concentration, but we also determine the actual function lambda dr. Now, just to show that it's not something rather nice and easy like 1/2 or e or pi, here is just the definition of lambda. So anyhow, you define some function beta k, and then you use it to define gk, and you take this definite integral, and that's the value of lambda. In fact, of course, the same applies in the Holroyd case for r equal to 2 and d equal to 2, but then very luckily the integral could be computed and turned out to be pi squared over 18. I mean, that's not what it looked like when they did it, because of course everything looked much simpler, but in fact the same would work here. Okay. Now, some different kind of percolation, different infection parameter. Let's take majority. Extremely natural setup. So let's take the cube, n-dimensional cube. It has 2 to the n vertices, and it's an n-regular graph, of course. And let's infect a site if it has at least n over 2 infected neighbors. And what can we say about the critical probability? Now, it's easy to see that it's about 1/2. So, of course, that's not what matters, but what comes later. So, with Rob Morris and really the two extremely clever collaborators proved that the next term is 1/2 root log n over n. And if you just tweak it a little bit by this lambda log n over whatever, then if lambda is smallish, it goes one way. If lambda is largish, it goes the other way. Okay, of course, an incredibly basic object. The n-dimensional cube is really what is more basic for a combinatorial is the power set. I mean, what should we know everything about it? But the cube, but the power set. Okay, but actually the reason I mention it today because there are connections with areas which other people have tried to do desperately. So let me mention Glauber dynamics. Actually, in the first case, I should just mention zero temperature Glauber dynamics. Who knows what Glauber dynamics is? Not too many. Okay, at least that, again, that much you should take away from the talk. Okay, so we have some ground graph, usually a lattice or whatever, and put an exponential, give every site, every vertex an exponential cone, which goes off independently of everything else from time to time. And now also let's give each site a spin, up and down, plus, minus, +1, -1, whatever. Okay, so that's our starting point. Now, of course, the whole setup leads to the Ising model, which was not constructed by Ernst Ising, but by his supervisor, Wilhelm Lenz. But it's always, I mean, it is the very famous in physics Ising model about which physicists and we know from more than about just about anything else. Actually, Wilhelm Lenz's supervisor, continuing the story, was Sommerfeld, whose picture I noticed outside on the wall. He was, I think, the most successful PhD supervisor ever in physics, theoretical physics. I mean, just quite mind-boggling the number of people and the quality of people he supervised. Okay, so what's the zero temperature Glauber dynamics? Every site is in a certain state, and then the clocks ring all over the place independent of each other. If the clock of a site rings, then the site looks around and goes into the state of the majority of its neighbors. Now, if it so happens that it has exactly as many neighbors with spin plus as with spin minus, then it tosses a coin and it goes into that state. So is this setup clear? So we have got infinitely many vertices. Each of them has a clock going off time and time again. And whenever the clock goes, it decides to change its state to the majority of its neighbors. If not, then it chooses tosses a coin. Or we can use whatever tie break we would like to choose. Now the question is choosing random spins at the beginning, with choosing sides with spin plus, with a certain probability at the beginning. What happens if we run the process? In what sense? Of course, we can ask lots of things, but the question we would like to know whether there is fixation. Now, what is that? We say that a graph for this dynamical process fixates at plus at a certain site x, if, when we run the process, eventually the site goes into spin, acquires spin plus, and remains, never changes the spin, its spin again. So it fixates at plus, if eventually after thousands of years, it goes into state plus, and then never changes it again. Of course, every site has its own time. It can't be that if we wait long enough, then every site will be in state plus, because that will never happen. I mean, it's obvious it will never happen. No matter how long you wait, some sites will be plus and some in minus. But every site by itself should go into plus and stay there. Okay, now the critical probability in this setup is the probability, the smallest probability at which the graph fixates at plus. So every site goes into plus eventually and stays put. Oh, okay, so again, which is the basic example, the d-dimensional lattice. Another very nice example, maybe even more basic, certainly simpler, not more basic and less important, is the d-regular infinite tree, which the physicists always call a lattice, the beta lattice, simply because it's much easier to work on it than on a normal lattice. There is no feedback on it. Okay, so lots and lots of excellent people worked on it. For example, Howard proved that on the 3 regular infinite tree, so every side has 3 neighbors, or if you draw it from top to bottom, at the beginning you have 3 neighbors, and then every side has only 2 children. So in this case, the critical probability is actually greater than half. And Caputo and Martinelli proved that it actually tends to 0. But the problem remains, what about other values of R? So for example, what about T4, just a 4 regular tree? Is it true that it's already 1/2? Or maybe it's bigger than 1/2, and then T6 will have probability 1/2. In all these cases, what do you expect? That dimension 2 is the first non-trivial case? Not so. In this case, even the case d equal to 1 is highly non-trivial. So all you have is the two regular infinite tree. What's the 2 regular infinite tree? Just Z. Every side has 2 neighbors. And actually it was Erdős and Ney who started the study, and then eventually it was proved. In that case it was proved what happens. But for D at least 2, there is an obvious folklore conjecture which really has been around for quite a while, that the critical probability for every D at least 2 is exactly 1/2. It doesn't tend to 1/2, it's exactly 1/2. Now, as it happens, it's trivial that it's at least 1/2 by symmetry, and also that at 0, it's at 1/2 it's 0. But the question is whether it is really 1/2. Now, how little was known, and this problem has been around for decades. Not that it was not known that it's 1/2, but it wasn't known that it's non-trivial. Maybe we were in the same silly case I told you about in the bootstrap percolation on the lattice. Maybe the critical probability is 1. Forget it. There is no genuine critical probability. And that was an event over 10 years ago. Fonches, 3 Brazilians, Fonches, Schoenmann, and Sideravicius, proved that actually there is a critical probability which is non-trivial. It's bounded away from 1. So for every d at least 1, it's less than 1. And what's the conjecture? That it is 1/2. So the least one would like that it's sort of getting bigger. Unfortunately, in their case, things go the other way. Not that epsilon d is getting bigger and is going to 1/2, but it was hurrying to 0 at an exponential speed. And still, it was true that it's always less than 1. Wonderful result. Okay, and now why did I mention the majority bootstrap percolation? Because Rob Morris proved recently that actually at least it goes to half, which is really infinitely better than saying that it's less than 1 and getting closer and closer to 1. It really goes to half. And that is proved by coupling. It's only the basic idea I'm saying. You know, you shouldn't think that on that basis you can reconstruct the proof totally far from it. But still, at the bottom of it, there was a complicated coupling argument of Larber dynamics and bootstrap percolation, so that our methods concerning concerning the majority could be applied. Okay, now let me just remind you of these 3 conjectures. So the first was the 3-neighbor bootstrap percolation on the cubes. What can you say about the minimum number of percolating sites? And let's say fixation of T4, the 4 regular tree, the 4 regular beta lattice, and the another Volcroft conjecture that on Z to the D it's 1/2 for every value. Now that has taken me to the end of the first half of my talk. And the second half, and then should have been the postscript, the actual proof. But I think there isn't much point in embarking on the second half. Let me just say 2-3 sentences about it. What did we do now? We had infection, spreading. If you have lots of neighbors, and then it changes its state, it becomes infected. What was the key? That once you are infected, you may remain infected forever. Now, suppose that is not the case, and probably the brain has very similar activities, but not quite like that. But when the instructions go out, suppose the instructions go out, that you have 6 infected neighbors and only 3 healthy neighbors, so become infected. And suppose the site obeys the instructions much of the time, but once in a blue moon, it disobeys it. It disobeys it, so it does the opposite. So there is a probability, small probability P of error. What happens then? And there the problem problem is just about hopeless. These are so random or probabilistic majority percolation is it's pitiful how little we know about it, but maybe if I find where I had a, let me try to, again, a stupid question. Okay, so now we have this, whatever, 32 by 32. That is, and then we take this time this probability at the bottom, the one I am moving now, is the probability of disobeying the orders. order. So it goes up to half because I mean, if you disobey it with probability half, then you, I mean, it wouldn't make much sense to disobey to probability 0.7. You may as well disobey the opposite with 0.3. So still, so there is a probability of disobeying the order, and then what happens? Let's. This is 32 by 32, and we are running it slowly. Okay. It disobeys it so much that it may as well be just a random flashing, plus minus plus minus. Okay, let's take it down. I mean, actually maybe it's better on 512. Let's try to do it on 512. And then I shall stop. Ah, I think it crashed. It's not nice that it does that. Okay, we are in 512. Maybe now it works. So let me take it with. So again, if it disobeys the probability 0.2, then you may as well have nothing. Now let's take out the value of disobedience to even. So 0.7, and then the whole thing starts to freeze. It will be a black empire and the green empire, and they are of course fighting for supremacy. Now it's pretty clear that black will win. So anyhow, what seems to happen, and we have partial results which were obtained with fair amount of work by Paul Ballister, Mark Walters, and Robert Johnson. That actually this is really the kind of thing that does happen. So it seems that there is a critical probability, which is something like 0.134. That if the probability of disobedience is less than that, then the system goes into an essentially all one state, and then remains there, or an essentially all zero state and remains there forever, and then suddenly there is a tunneling from the essentially all zero. Suddenly you flip to all one, and then you stay there ad infinitum. And we could prove it for tiny probabilities, depending on the value of n, so even smaller. But this is one of the cases where the theoretical result is way ahead of simulation. I mean, there's absolutely no chance of simulating what we have proved even on the 10 by 10 square.
So what's the underlying process here? I mean, you're disobeying which rule here?
Just straight majority. Here we are disobeying the straight majority. So every site has, let's say a site is black, and if it has two black neighbors, then the rule is at the next time step remain black.
Right, okay.
For tie breaking, it's better, we may as well use the site itself. So every site has 5 neighbors itself, and the 4 things on this torus. And the rule is, the deterministic rule would be go into the majority. Now the disobedience is, yes, go into that one, but with probability 1 minus p. And with probability p, do the opposite. And of course, now the probability of disobedience is 0.7, and it's pretty clear that green empire has lost. It will go into essentially all black, but it can't be all black because there is the disobedience. So even at the very end, we must have 0.7% of the sites in green. But then it will stay there forever. I mean, there's no way we could wait long enough to find it. I mean, till it flips. But when it flips very quickly.
But you're claiming you proved that it does.
We proved it. Yeah, yeah. No,
right.
that is proved, but only for tiny probabilities. So tiny that it depends on n. So it's the totally open question that there is a genuine critical probability which is independent of n. In fact, we somehow suspect that it's about 0.134 or such things.
But what's n in this picture? Is n2?
N is 512.
Oh, n is 500.
So we have got here 512 square sites
Okay.
in this picture. So it's a total split 512 square sites. And of course, if you take it above it, and very quickly, black ruled, but after a little while, I think even by now, I can't tell whether there are more black sites or green sites, and it remains in that one essentially forever.
But you're saying if you made it really tiny, like much smaller than you had before, then it would actually essentially become all black, and then at some point flip to
Yes,
green quite
yes,
quickly.
yes,
Right.
yes.
That's
Of
what
course, if the probability is closer to the supposed or conjectured critical probability, the same thing should happen even quicker. Of course. But it's wide open. So as I was saying, the blessing in normal bootstrap percolation is monotonicity. The other blessing is inflection parameter 2 or inflection parameter D. We are totally in deep waters if the inflection parameter is somewhere between 2 and the dimension, and we are in even deeper waters if we introduce any kind of random recovery, which can be viewed as random recovery or random disability. Okay, I doubt that I shall see proof of many of these results, although I still hope that of the 3 I mentioned, maybe at least 2 will be solved. Here, I would be absolutely amazed if the actual critical probability could be proved, because even much easier results have immensely complicated proofs that most people don't believe. Okay, thank you very much.
Thank you very much. Any questions, comments, questions?
Do you have any understanding of why it changes? I mean, when the probability is so low, it changes from essentially all black to green. It seems very surprising.
Yes. Because it can change only in a certain way. I mean, the tunneling has to go in a very deterministic way, and and if that happens, then it has to hurry. If it gets derailed, bang, it goes back. It flicks back, as if it tries to jump out of the water. And I mean, pulling. I mean, cannot. I mean, once in a blue moon, it gets detached, and then it goes across. Well, we found it very surprising, but in fact we can determine the actual time it takes pretty well. So also we determine the actual eternity, how long it stays in essentially all zero configuration and essentially all one. But the time differences are absolutely immense. So almost always zero, almost all zero, and then a very quick change, tunneling from all zero to all one. Now, no, it is very surprising, which is why we like the result. But of course, we would love to prove that there is an actual critical probability where these things do happen independently of the size of the torus. Yes, yeah.
It seems to me that in this field, the questions often, like, they're easy to explain, but they might be really hard to solve.
Yes.
But then maybe a clever trick or something might solve it. So you said...
Here there hasn't been any example where there is a trick, what you would call a clever trick.
No?
Here the clever tricks take 60 pages to.
So how do you judge whether, so you said like some questions are harder than others?
No, come on. Those were, those were for your delectation. They were for entertainment. Those were baby questions. So these were not, the questions at the beginning were not research questions.
Yeah, but I mean, when you said that there are like simpler questions that have had very difficult proofs, for example, how do you kind of know that, how do you rank the questions in difficulty?
How did you know that Fermat's last theorem is not a triviality?
Oh, exactly.
Exactly. So you often at the beginning you can't tell. How could you tell that even this three neighbor question, which really seems so near to the questions whose answers are easy? How do you know that it's non-trivial? You don't, except that lots of clever people have tried it and have made no dent in the problem. So I don't quite see. All these are very, very basic questions. Even what about the four regular infinite tree? What is a nicer object than a four regular infinite tree? It's an incredibly nice. As nice as things go, and the process itself is extremely nice, and still we know essentially nothing.
So if you have a rule for recovery rather than just probabilistic recovery, is that a completely different problem? Or is it harder?
They're different problems, but they tend to be much easier.
Much easier?
Much easier.
Right.
Much easier. You could introduce recovery, that every site recovers with a certain probability. You give it a probability distribution of recovery. That is, again, much easier.
Right.
The difficulty here was that the rules were disobeyed. Not.
Yeah.
But even there, of course, and the questions are very different. You can't ask when do you get full percolation. You would have to ask very different things. But those also tend to be, in fact, they are often quite a bit easier than the questions I talked about. Sorry,
maybe a simple question. Do the physicists deal with the same kind of things?
Yes.
And
they were all physicists.
And what are the methods? Are those the same methods they use?
Not quite. Because of course they. Not really. Eisen and Leibowitz did essentially proper mathematics, and they are really very high class mathematical physicists. But often physicists like just internal consistency. They postulate that this happens, and then use this postulate to deduce various other assertions, and if they find that everything is consistent, then they are happy. For example, in this lovely Holroyd result, pi squared over 18 over log n. Of course, the physicist knew what the answer was, except it was wrong. Except it was wrong because in this part of the world, simulation is out. It's much less out there than in the kind of things I talked about at the end. But even there, they got the constant completely wrong. And of course, the proofs tend to be like all there have been hundreds of papers on percolation, mostly by physicists and some by computer scientists, estimating this and that, and often you find papers that contradict each other.
So they don't have sharp results like this one by just using physical methods and
No, by very far from it. No, it's a completely different thing. Yes?
Are these problems only investigated with 2 different states, or do you also look into more states?
No, they tend to be, I mean, the whole point that there are so many difficult unsolved problems about 2 states that nobody is expecting qualitative difference between 2 states and 25 states.
Right.
It won't, I mean, you can after all, the whole thing can be encoded in instead of having 25 states, you take groups of sites and then they tell you the states. So it really is very, the difference is very little, very little, having many states. When you want to define various things, then actually it makes a difference. So occasionally there are cellular if you wanted a one-dimensional cellular automata with, because if you forbid little longer range interactions, and why not? I mean, you could say that no, they really go just very close. In that case, the number of states helps. So one of the results I would have mentioned that 10 to the 30 states. But in some sense it's the same. No, it is exactly the same as saying taking groups of sites and saying that every site in that group is in one of 2 states, and then you have got infinitely many states, and your various groups are called by the same name. Yes.
Maybe an unrelated question, but what software or language do you use?
Wrong. For what? Wrong question. I emphasize that the problem that this was written by Paul Ballister. I'm so sorry. I'm a pure mathematician. but I've got lots of clever students who actually love writing very efficient programs for all kinds of things. So, no,
Okay, so just the last question. Yes, the last one.
So when you say that if you turn this probability down enough and wait a million years, it'll suddenly switch from all black to all green, do you mean that the time it takes to do that is significantly qualitatively less than the time it would take for everything to disobey at once by coincidence?
Oh yes, much less.
It's completely different.
No comparison.
Okay.
Absolutely no comparison. You are right. I mean that would be one way of doing it. Every side decides to disobey or go the right way. Yes. No.
But the time
It's
it
completely
takes, the time it
different.
takes to switch, does that depend on n?
Yes.
It does.
Yes. It has to, because in a way the switching will happen in a strip, and once the strip manages to change, then it can spread fairly easily. But first you need little units which are fairly sturdy. The trouble with changing at random somewhere, if you change to green in the middle of a black sea, what happens next time? You change back to black. Or if not next time, you change back to, after 5 steps. So it's impossible to go against the trend and survive. The problem is exactly survival. So you need some little sturdiness built in, which will enable you to survive to the next step with some probability and then spread.
Thank you very much.